Okay, so let's review really quickly what a reciprocal function is before we go into graphing it, which is what we're going to be doing in this video. A reciprocal function is any rational function where the denominator is linear, right? Degree of 1. So the denominator is linear and the numerator has a degree of 0. It's a constant. Okay, so that is a reciprocal function. A reciprocal function is a rational function. It is just a special type of rational function. The name of the graph, we didn't really go over that, but the name of the graph is a hyperbola, which we've seen, right? We've seen hyperbolas before that look like this. The asymptotes are where the restriction of the domain is and the restriction of the range are. Now, what's important here is that as the function moves, the asymptotes move with the function, just like it did with exponentials, right? When we had an exponential function that moved up 1, the asymptote also moved up 1. Okay, so let's look at what this looks like on Desmos. So this is your parent function, y equals 1 over x. Okay, so y equals 1 over x is this dotted function right here. So if I click this, it just got graphed on top of let's go here, on top of the dotted function. Okay, so then the question is, what happens when we have something like, I put a 2 here. Actually, just kidding. We're not going to do the 2. We're going to do, what happens when I put a 2 up here? So instead of a 1, I put a 2, or a 3, or a 4, or a 5, or a 6, or a 10, right? So from 1 to 10, what happened? Well, you can see that it basically, so this whole thing right here became less, in a way, steep, right? It became a little bit further out. It expanded is the word, right? It expands when you put a number that is bigger than 1 up here. Basically, you're multiplying. That's your a value. Kind of like in a quadratic function or any other function that we've done at this point. When you put an a value, it stretches the function out, right? It stretched it out. I took this and I pulled it, right? Like a rubber band. When you pull a rubber band, it stretches it out. Okay, so if I put like 100 there, you can't even see it because it stretched it out so much. Okay, so that's important. The a value stretches it out. Okay, now what happens when what do you think is going to happen if I add, let's, oh, let's turn this off. If I add, let's do on the end. If I add 2, what happens if I add 2 on the end? Well, let's think about what has happened in the past when we add 2 on the very end of things, right? It is going to move it up 2 units, right? So the function looks exactly the same, except it literally went from here up 2, right? From here up 2. Every single point on the graph went up 2. Even here, it went up 2. Now, is x equals y equals 0, so the x-axis, is that still the asymptote? No, because look, it crosses the x-axis here. So it's not an asymptote. Where did my asymptote go? Well, my asymptote also moved up 2. So technically, x or y equals 2 is, let's go like that, is my new asymptote. So it looks a little messy, but let's go here. You see how that's the new asymptote? It's now infinitely approaching x equals or y equals 2, and no longer, like this function, is it infinitely approaching y equals 0. So your asymptote moves with the function. Now, did the function move right or left? No. So my vertical asymptote is still the same. Then the question becomes, what happens if I add 2 on this end? It is going to move left 2, right? Remember, when it directly affects the x, it does the exact opposite of what you want it to do. The analogy I've made in class time and time again is your x does not what you want them to do, right? Your x will usually do the opposite of what you want them to do. So the x, anything affecting the x, is going to do the opposite. Okay, so if I put plus 2 on the x, horizontally, it's going to go the opposite way. So it went left instead of right. It goes left 2, and our horizontal asymptote, so x equals -2, it moved with the function. So let's move this. So you see how the horizontal asymptote, I keep getting my words mixed up. My vertical asymptote moved with the function, right? Because what value of x is going to make this function right here undefined? X equals -2 is the value that's going to make this undefined. So therefore, that is my vertical asymptote. It cannot cross that value. It doesn't exist at that value. So what happens if I have a +2 and a +2 and a 5 here? Well, three things happen, right? It expands, it moves left 2, and it moves up 2, right? So here's my original function, and look at my new function. You know what? Let's keep this as a 1 just to see this. Now, again, it moved left 2 and up 2. And remember when we learned about hyperbolas with conics? This is like my center point, my HK in a way, right? So technically, my HK, right? You see how here HK is going to be -2, +2. It is my center. So let's put this on where we have these sliders. Right now, my A is 1, right? A is 1, H is 0, K is 0, which means that my function is 1 over x. 1a x minus 0 plus 0. So h and k technically disappear. Just watch what happens as a goes greater and greater and greater and greater, right? You see that steepness happening? It like losing its steepness. It's stretching out. Now, what happens as we go into you see it's getting closer and closer. A cannot equal 0. It's no longer hyperbola, right? Because 0 over anything is going to be 0. So it just becomes a constant function. What happens when it goes negative? It reflects. And this is really important. When we go negative, it reflects technically over both axes, but really what it's reflecting over is the x-axis. Okay? So it's reflecting over the x-axis. As A becomes negative, it reflects over the x-axis. Isn't that kind of cool? It's like hypnotic. Okay, we're going to stop. All right, let's go back to 1. Okay, now what happens as h gets bigger? So as h gets bigger, x minus h, it's going to go to the right, right? If this was a plus, then technically it would be going the opposite way, right? But because I made it a minus, it automatically goes in the way that you think it's going to go, right? So x minus 2.2 goes 2.2 to the right. All right, this just moves the function right and left. Let's go back to 0. And then k is going to move it, what do you think? Up and down, up and down, up and down. So if I move all of these, crank them all the way up, right? All it did was move it all the way to the right, all the way up, and it stretched it out. If I move it all the way down, right, it flips it because it gets negative. It's also stretched. It goes all the way to the left and all the way down. So here's my function. So just understanding what each thing is going to do. Now, I just want to add that what happens if I turn, so we already saw what happens when I turn this value negative, right? If I make, hello, if I make x negative, 1 negative, it flips over the x-axis. What happens if I make x negative? It does the same thing. However, if I have a +2 here, and I now make this negative, it is technically when you make x negative, it is flipping over the y-axis. Look at the difference. See how it flips? it is technically flipping over the y-axis. Versus if I do this here, you see how now it's flipping over the x-axis. There's your x-axis flip, not your y-axis flip. Your x-axis flip. Whoop, whoop. And here's your y-axis flip. So here's the moral of the story. If you're directly affecting the x, it is reflecting over the y-axis. If you're directly affecting the entire function, this negative makes the entire function negative. Therefore, it's turning y negative. Y is the entire function. Then the function is flipping over the x-axis. But it makes no difference when we're dealing with the parent function because flipping over the x-axis and flipping over the y-axis is the exact same thing because they're symmetrical. So this is the little spiel, exactly what I just explained, right? A over x minus h plus k, where h moves it right and left, k moves it up and down, and a stretches it or shrinks it. And then if you put a negative in front of x, it flips over the y-axis. We've done this for like 75,000 functions, right? What are other functions we have done this with? Oh, my tablet's not plugged in. Un momento, por favor. Okay, so what are other functions we have done transformations with? We have done them with quadratics. We have done it with square root functions. We have done it with cubic functions. We have done it with absolute value functions and exponential functions. I think that's it. Maybe I'm missing one or two, but we've done the exact same thing for all of these functions. It's literally the same ground rules, just when you directly affect the x value, it goes right or left. It goes the opposite of what you think it's going to do. When you directly affect the y or the entire function, it goes up or down. When you multiply the entire function by a value, which is what this does, it stretches it or shrinks it, and it flips it. It can reflect it over the x-axis. Okay, all the same rules. So let's talk about this. First thing you're going to do is you're going to find the domain, right? So my domain is going to be all real numbers, but x cannot equal what? 4. I set x plus 4, x minus 4 equal to 0, so I get x cannot equal 4 technically. So I know at x equals 4, I'm going to have a vertical asymptote immediately. Okay? Then I also know that my function moved where? Up 2, so I know I'm going to have my y equals 0 asymptote became a y equals 2 asymptote. This is x equals 4 and y equals 2. And right now, I'm not worried about you graphing it perfectly, but I do think it's important for you to get like a few of the key points. So I'm going to get my y-intercept here, right? So my y-intercept, because I think it's important for us to know where it is. Now, it's not negative. So I know it's still going to have the this and the this in the same form. So I'm going to find my y-intercept. I know it's going to be here somewhere. So my y-intercept, I just plug 0 in. So I get 2 over negative 4 plus 2. 2, so y equals, I put a 0 in here. So 2 over negative 4 is negative 1/2 plus 2, which is negative 1/2 plus 2 is positive 1.5. So my y-intercept, what color do I want to graph this in? Let's do blue. So my y-intercept is going to be 1.5, right? I could solve for my x-intercepts, but we're not going to do that right now. So right now, all I'm going to do is get at least that 1 point. Right now, we're not going to focus on getting a perfect graph. We're just going to focus on sketching the graph. Eventually, we're going to get the perfect graph, but for right now, we're not going to. And I know that this is going to be reflective of it. It's a reflection. So technically, I know it's going to be a little bit more out there because these should be equidistant from here. So there's your sketch of the graph. It is not a perfect graph. We have not plotted points. I'm just getting you guys used to what it's going to look like. So let's look at this one. So my domain, first thing, domain. And I use red now because it's the red flags, right? So what can it not be? Stop sign. So x cannot equal -1. It will always be one value for reciprocal functions because the whole point of the reciprocal function is that it is a degree of 1. It is linear. There's only one x value that it can be. So I'm going to go here. Boom, 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 boom. There's my asymptote of x equals -1. And then I also know that it went down 4. So I'm going to go here. Boom, 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 boom. Y equals -4. And it flipped. Please notice this. It flipped. So I know it's not going to be here anymore. It's going to be here and here. So what's my y-intercept going to be? Well, if I plug in 0, I get -3 plus 1. Whoa, -3 over 1, which is -3, -3 minus 4. So my y-intercept, so x equals 0, is -3 minus 4 is -7. So 0, -7, which is not even on this graph, but we can pretend. It's going to be, here's 6, here's about 7. So it's going to be like here. So that gives us a little bit of room for understanding the distances. A little bit, not really much. But again, we're just getting used to finding things. And then we're just gonna, now we know it's not gonna be super close because in order for it to be super close, it's gonna be a smaller number than 3. Remember, 3 stretches it out. It gets this a little further away from the origin. I don't like this, so let's redo this a little bit. Whoop. So this is about this far, so it's gonna be somewhere here. There it is. It looks something like that. It's not perfect. Again, this is just a sketch. Now, your work for this is going to be on Desmos, so you're going to be able to play around with the function kind of like how we did here. Okay? Where we were kind of like, okay, well, we have a 3 and a 4 and a 7. Also on Desmos, you're going to be restricting the domain. We did, it's the same thing that we've done with exponential functions. We did it in class. So if I have like x is less than 6, it restricts my domain, so it stops the function at 6. You see how it says 6 is undefined? Because technically, if I didn't put equal to, now 6 is defined, 6, 1.